and when you connect an OpAmp to a circuit, you will have to consider these parameters of the OpAmp, and that is the topic we are going to discuss today. So, the non-ideal effects of an OpAmp have certain limitations on the characteristic of an OpAmp. Because of these non-ideal effects, we have to look into the consequences. Because it is not an ideal OpAmp, so far we have been discussing, all the analysis of our discussion was based on an ideal OpAmp, but practically when we connect it in a circuit, we are not going to have those ideal effects. We will be getting non-ideal characteristics of the OpAmp. So, what are those parameters that are there for a practical OpAmp that we are going to discuss today? So, the ideal OpAmp consideration when we had earlier, we had that the input of the OpAmp, input voltage which we apply to an OpAmp, we did not have any limitations, or we did not consider any limitation on the input voltage which is given to an OpAmp. But practically for an OpAmp to operate properly, that means for proper transistor biasing and linear operation, because in the OpAmp what is there? There inside the OpAmp, the circuit in an OpAmp will be having transistors, and so the linear operation of the transistor is one important thing. Then only we will be having the distortionless output, and also the biasing we have to take care of in transistor. That is why we have to consider this input voltage limitation in an OpAmp also. So, when you apply the common mode operation of the OpAmp, that means we are suppose giving a DC voltage which is common to both the input terminals of an OpAmp, we cannot give any arbitrary or any value of input voltage. So, the common mode operation will be having a limit, and that maximum limit is given in all the OpAmp data sheets, it is available. How much input voltage you can apply in the common mode? Suppose if we are applying 741C, that is one IC having OpAmp, because integrated circuit of the OpAmp has this number 741C. Then in 741C OpAmp which we use in the lab, that will be having a limitation of this maximum common mode input as plus minus 13 volt. That is, we cannot exceed this limit, and if we will exceed this limit of plus 13 volt or minus 13 volt given to the common mode, in common mode operation to the OpAmp, then we will be not getting proper transistor operation of the circuit in the OpAmp, and that will be not linear. That is why the input voltage has a limit in OpAmp. Another limitation on the OpAmp is as per the output voltage. That is, the output voltage of an OpAmp cannot exceed the DC supply voltage. If we consider an OpAmp IC, for example 741 IC, that is the integrated circuit having OpAmp, then the voltage which is to be applied is plus 15 volt and minus 15 volt, VCC and minus VCC. These voltages are to be applied in an IC, there are pins for this. So, generally in 741 it is up to 15 and minus 15, I mean it is it should be around plus 15 and minus 15. So, now the output voltage V naught which we will be getting for the OpAmp, it cannot exceed this supply voltage. For example, we consider an OpAmp having a voltage gain of say 2 into 10 to the power 5, and the circuit is for an example we are taking an open loop circuit, that is the open loop gain is 2 into 10 to the power 5. Now suppose we want to amplify a signal which is say 2 millivolt. The signal which is given at the input is say 2 millivolt, that means 2 into 10 to the power minus 3 volt, and suppose it is an inverting connection or inverting type of op-amp we are connecting. Now if we consider this voltage given at this inverting terminal say, which is 2 into 10 to the power minus 3 volt, what will be V2 or output voltage? V naught. V naught is the output voltage. What will be V naught? So theoretically we should get minus A into Vi, that means minus 2 into 10 to the power 5 into 2 into 10 to the power minus 3. So that means minus 4 into 10 to the power 2, it's 400 volt. But this 400 volt at the output is not possible because we are having the supply voltage given by 15 volt. So it will be not reaching that 400 volt. So what will be happening is that it will be saturated, the output will be saturated at 15 volt, and it is not exactly actually 15. Every op-amp has the output voltage rating given, and for a 741 op-amp, 741 IC which is having that op-amp, the maximum output voltage can be between plus 13 and minus 13 volt. That means it cannot go beyond plus 13 volt and it cannot go down below minus 13 volt. So suppose if we are applying two AC signals at V1 and V2 and the output we are going to find out, then the swing at the output V naught will be having a maximum swing of 26 volt. That means it will be between plus 26, the swing will be this swing, if we consider V naught, it will be between this plus 13 and minus 13, that is 26 volt will be the swing possible in the output. So this limit is there coming from the consideration of the output voltage because it has a limitation given by its supply voltage. Now other practical considerations are the open loop voltage gain that we were considering earlier in ideal case to be infinite, but that is practically not true. We will be having a finite open loop voltage gain. We do not get infinite open loop voltage gain as we considered for the ideal op-amp. Similarly, the input resistance and output resistance which we considered for an ideal op-amp as infinity and 0, but practically we do not get that infinite input impedance or resistance and we do not get 0 output resistance. What is exactly obtained is that input resistance of an op-amp is not infinite, it will be having a finite value. Of course, it is large, but it is not infinite, and also the output resistance is small, but it is not 0. It may be in the order of ohms, but it is not 0, and the input resistance may be in the order of meg ohms, but it is not infinite. Another important figure of merit or one important parameter that comes from actually the bandwidth. In ideal op-amp we consider that the bandwidth is infinite. That means over the whole range of frequency we will be getting the same characteristic of the op-amp. They do not drift or they do not change over frequency range, whole frequency range, but practically that is not the case, and we have a finite bandwidth. If we consider the frequency response of an op-amp, we will find that the gain will vary because of capacitances etc. existing in the actual op-amp circuit. That is why the gain will not be constant, which should be the case if we have an infinite bandwidth, but practically in the high frequency range we will be finding that the gain will be dropping. So the bandwidth is not infinite, it is a finite bandwidth in the practical op-amp. Similarly, one another important parameter which we have to consider while practically dealing the circuit or using it in a practical application is the slew rate. So, what is a slew? What is that slew rate mean is that the slew rate is the maximum rate of change of output voltage per unit time. Now, actually that determines how fast the output voltage can change, because we have suppose an input voltage given to the input of the op-amp whose frequency is very high. Now, at the output side also we expect that the voltage should change at the same rate, but practically this is not the case. There is a limitation on how fast the change can occur. That means the maximum rate of change in the output voltage is limited. So, even if we have a very high frequency input voltage, at the output we will not be able to get that at the same frequency, and that is why if we have a very high frequency signal, at the output we may get a distorted signal because it will not be able to follow the frequency of the input signal because of this slew rate. And generally if we consider a 741 IC, it has a slew rate given by 0.5 volt per microsecond. That means 0.5 voltage per microsecond. That is the maximum voltage change per unit time that can happen in a op-amp given by 741 IC. So, that means that in 1 microsecond the change can be maximum of 0.5 volt. If we have more than that, we will be having a distorted output. So, that has to be kept in mind. Similarly, some other important parameters that we have to know about is the input offset voltage and the input offset current. Now, what is an offset voltage or an offset current? Basically, this comes if we consider the circuit of an op-amp. It is nothing but differential amplifier, what we have initially discussed about. So, we have transistors which are perfectly matching, that is the requirement. If the transistors in the differential amplifier are perfectly matching, that means the same collector current, same base current, and the resistances which are connected are also exactly same, then the offset voltage and current will not appear. This is the DC condition, mind it, this is coming from the DC condition of the differential op-amp. So, let us again see an op-amp circuit. Here in this op-amp we are connecting the inverting and non-inverting terminal to ground. So, expected output voltage should be 0 because these both are 0. So, differential voltage is 0. So, what we should get at the output? We should get 0 voltage, but practically this is not so. If we ground both the input terminals of an op-amp and see measured output voltage, you will be getting a very small although voltage, but it is not 0. And why this is happening? This is happening because of non-matching of the transistor in the differential amplifier, because if we consider the differential amplifier circuit again, we see here that the two transistors Q1 and Q2, these two transistors are connected to same resistances RC. Now, if Q1 and Q2 are exactly balanced or they are matched, that means their collector currents are same, base currents are same, then there will not be any voltage appearing at the output under DC condition. That means if we have the voltage across this RC and this voltage across this RC are same, V01 and V02 same, without any signal, of course you are not applying any signal, just we are having their say grounded, then V01 and V02 should be same and that output voltage should be 0. But practically that does not happen, because although we expect that the two transistors, even if you use the same IC, we expect that the transistor should be, these transistors should be matched, but that practically does not happen. So, because of this imbalance between the collector currents, the voltages at these two across these two resistances will not be exactly equal, and that is why we will be getting a non-zero voltage at the output, because V naught 1 and V naught 2 are not exactly equal. So, V naught 1 minus V naught 2, that is what is at the output available V naught, that will not be equal to 0. So, due to this offset voltage, the input offset voltage, we will not be getting the output voltage 0 when you simply ground the input terminals. That means there is an output voltage, offset output voltage. Another factor is that due to the input offset current, presence of the input offset current, and that happens because the base currents in the two transistors are not exactly equal. IB1 and IB2, if they are not exactly equal, then due to the unbalanced base currents, there will be a current at the input terminal of the op-amps. That means here there will be a current in the input terminal of the op-amp, unbalanced base current will be there. So, because of this, as these two base currents are not equal, so due to the unbalance of these two input base currents, we will be getting an output voltage. So, that means we have the output voltage available even if you make the input terminals grounded. This is because of the two reasons. One is due to the input offset voltage PIO, suppose we are naming it, and the other is due to the input offset current IIO, and that happens because of mismatching of the two transistors as well as the input base currents of the two transistors not being equal. Because if the input base currents are not equal, there is an unbalanced base current, and which will be creating an output voltage. Now, if we consider only say the input offset voltage, we want to show what will be the output voltage. The input offset voltage is shown by a source here, and the polarity of this input offset voltage is not fixed. That means depending upon which transistor has unbalanced collector current more, that means which transistor has a collector current higher, the polarity of the offset voltage will also be accordingly. It may be positive, it may be negative. So, if we consider the output voltage due to this input offset voltage alone, then it is like a circuit where we are having already a source. So, now if we consider only the non-inverting circuit of an op-amp, suppose the non-inverting op-amp has a resistance, feedback resistance RF and R1, we are not applying any input signal, but this input signal is available because of the input offset. So, input offset voltage is there, and if we consider a non-inverting op-amp, then the output offset voltage V naught OO, that will be simply VIO into 1 plus RF by R1, as if it is having a source. Exactly this is coming from the input offset voltage, because of which we are getting an output voltage even without a signal. So, we are having already a voltage at the output even though both the input signals you ground, and that is why we have to compensate this output voltage. Whatever the output voltage is coming, if we measure it, then we have to compensate it by properly designing a compensating circuit so that this offset voltage can be balanced. Then the exact circuit analysis or proper behavior of the circuit which we are using can be determined, because we have to somehow get rid of this offset voltage, otherwise it will be hampering or it will be interfering in the actual output voltage which we are going to get when we use the op-amp in some practical consideration or in some practical circuit. And there are ways to overcome this offset voltage, but we are not going to discuss those details. Only we want to emphasize that there is a DC condition already prevailing, means we have a DC voltage already at the output, that is called the offset voltage, and that is to be first of all balanced. Now, typical values of this offset voltage and current at the input for a 741C, if we consider around 6 millivolt input offset voltage is existing, and if we consider the input offset current, maximum can be 200 nanoampere. Both are of course DC voltage and DC current. These are coming from the unbalanced or imperfect transistor matching in the the differential amplifier circuit. So, these are the typical values. Maximum 6 millivolt can be the input offset voltage and maximum 200 nanoampere DC current may be there in as of input offset current in 741 IC. Now, if we consider a practical op-amp and we draw the equivalent circuit, then we get such a type of circuit where inside the op-amp we are considering this op-amp by this symbol, this is the op-amp, but inside this op-amp we are having an input resistance Ri which is not infinity. So, we are having a finite value of Ri and we are getting at the output side we are getting the output voltage which is given by AVOL into VID, VID being the differential voltage at the input and multiplied by this open loop gain of the op-amp which is AVOL, which is very high, but it is not infinite. Maybe it is 2 into 10 to the power 5 typical value. So, multiply it by this difference in voltage at the input terminals, we get the output which is shown here by a dependent voltage source. Apart from this output voltage, there will be a resistance which is R naught, which is the output resistance of the op-amp, and that is not 0, that is having a small value maybe in the order of ohm, and typical value is a 75 ohm, but this is not 0 and this Ri is not infinity. So, the practical op-amp circuit will be something like this. Now, we will be considering this circuit for our analysis because we are considering a practical op-amp, and if we now consider this circuit and we want to use this op-amp for, say for example, a non-inverting op-amp or non-inverting amplifier, then we will have to consider these parameters. It is not an ideal op-amp, mind it, now we are not having an ideal op-amp, but we are having all those parameters. So, now let us take this and we are going to now see what effect we are having in the circuit which we are going to use because of these non-ideal parameters. So, for example, we are revisiting the non-inverting amplifier and we will be finding out the closed loop voltage gain. And why we are calling it a closed loop? Because we are having at the output a resistance which is say R2, that is the feedback resistance, means it is having a part from output to input. That output to input part is called feedback part, and that is why this circuit is a closed loop, it is in the form of a loop, it is not open loop. If we do not have this resistance R2, then it will be not closed loop, but because of this resistance in the backward or feedback loop, another resistance is there, of course R1. So, there is a part from output to input which is known as closed loop. Now, in this type of circuits, when we are having an inverting terminal or the negative terminal, a feedback part or a feedback resistance loop given by R2 and R1, we will be getting a negative feedback effect on the gain. And how we are getting a negative feedback, how the output voltage is negatively coupled with the input, that we are going to see now, and what is the effect of this negative feedback gain on the gain of the op-amp, that also we are going to discuss. Now, if we look into this circuit, this is a non-inverting amplifier circuit we are taking just as an example, we are taking this non-inverting. In all the applications which we are earlier discussing, like non-inverting, inverting, differential, integral op-amps, etc., there everywhere you will be getting this effect. If we have a negative feedback, there will be an effect on the gain also, but we are considering as an example the non-inverting amplifier and see the effect of this negative feedback on the gain of the op-amp. In this circuit, now we are having two resistances R2 and R1 apart from this op-amp, and we are connecting a signal Vs at this non-inverting terminal. So, the op-amp circuit will be redrawing by using the equivalent circuit. So, the whole circuit will be like this. Now, we are having the op-amp circuit given by the input resistance Ri, the dependent voltage AVOL into VID, where VID is the difference in the voltage between the two terminals, positive and negative. The voltage here is V1 minus V2. If V1 is the voltage at this positive terminal, V2 is the voltage at this terminal, then VID is V1 minus V2, which is the difference in voltage. And that difference voltage is amplified by this open loop gain of the op amp, which is AVOL. So, we are having this dependent voltage source. Apart from this, the resistance R0, which is having a small value no doubt, but it is existing. So, that is there, and R2 and R1, the feedback resistance are there because we are having a non-inverting amplifier. So, these R1 and R2 will be there as connected to the inverting terminal. And now, if we look into this part from the output to the input, this is the feedback resistance R2, here it is connected to another resistance which is grounded, and both of them are connected to the negative terminal. Now, output voltage is V0. We have named the voltages at this inverting and non-inverting terminal as V1 and V2, and the signal which is applied at the non-inverting terminal is Vs, that is the applied signal. We want to get an amplified non-inverted output at V0, that is the non-inverting amplifier. Now, if we denote the currents flowing in the circuit, let us name the input current coming from the sources II and output current is I0. It is going out of the op amp. Now, at this point the current will be flowing down because we are having an open loop here, there is no other resistance to ground. We are considering the open loop case, means open loop means there is no load here, no load resistance. There can be a load resistance at the output, but for the time being here we are not considering that. So, this current will have to follow a closed path. So, it will be flowing in this direction. This is I0. At this point there will be two branches, one will be going this way, which is say I negative. I am denoting it by I negative because it is entering the negative terminal, and the other part is IR1, which is flowing through R1. The current which is flowing through R2 is I0, the current which is flowing through R1 is IR1. Now, this is the whole current flow direction in the op amp. Now, here we will be finding out the output voltage. So, what is the output voltage for this non-inverting amplifier? If we look into this circuit, V0, this voltage is nothing but AVOL VID minus the drop in the resistance R0, because the output resistance R0 is there, it is not 0. So, the voltage which is available at this source AVOL VID, VID being the difference in the voltage. So, we are following the op amp principle that difference voltage is amplified by the open loop gain AVOL VID minus this drop is I0 R1, I0 R0, that is V0. So, V0 is equal to this. Now, here we will be making one approximation which is a valid approximation, we can cross verify also. The approximation is that as this R0 resistance is very small as compared to R1 and R2, R1 and R2 are generally in the order of kilo ohms and R0 is only in the order of ohms. So, effectively this R0 is very small than R1 and R2. So, the drop I0 and I0 R0, this drop we will be neglecting here. So, then we will be getting V0 equal to AVOL VID, and VID is nothing but the difference between these two voltages V1 and V2. So, AVOL into V1 minus V2 is equal to the output voltage. Now, V1, if we look into this, V1 is nothing but Vs. So, replacing V1 by Vs, we get the output voltage V0 equal to AVOL into VID means V1 minus V2 and V1 is equal to Vs. So, it is Vs minus V2. Now, you look into what is V2. The voltage here is V2. Now, this voltage we have to find out. Now, again if we look into this part, the current part, the current is divided into two components here and here. So, the voltage at this point V2 is exactly equal to IR1 into R1, IR1 into R1 is V2. But again we will be making one valid approximation, the approximation being that this current which is flowing I minus or I negative, the this current is very small, because if we consider this resistance Ri, this is very high. This Ri is very high. That means, if we consider these two resistances Ri and R1, here the current has two parts, one is this through Ri and the other is through R1, but this resistance is very high. So, we can practically assume that all the current that is flowing is through R1. That means, the same current I naught is flowing through R1 also. I dash, I negative is almost equal to 0. That approximation we will be using, and then our task is easy, because if we want to find out this voltage, the voltage division is taking place, the same current flows. So, V naught into R1 by R1 plus R2 becomes V2. So, here we are using that approximation, and that approximation is exactly valid, because R has a very high value, it is in the order of megohms compared with R1 or R2. So, then I dash is very less than I R1 and make it equal to 0, and then we get V2, which is equal to V naught into R1 by R1 plus R2. So, if we write down V naught from this expression, that AVOL into VID, that is equal to V naught, VID is nothing but Vs minus V2. So, Vs minus V2 is replaced by this quantity V naught into R1 by R1 plus R2, or if we transfer this part having V naught to the left side, take common V naught, it will be 1 plus AVOL into R1 by R1 plus R2, that is equal to AVOL into Vs. And so, our interest is V naught, that quantity we want to find out. So, simplifying this a little bit, that we get is V naught into R1 plus R2 in the denominator, in the numerator it is R1 plus R2 plus AVOL R1, that is equal to AVOL into Vs. So, now what will be V naught by Vs, because that gives us the overall gain AV. So, V naught by Vs, if we find out from taking the ratio between V naught by Vs, it will be AVOL divided by this whole quantity. So, that is equal to AVOL into R1 plus R2 by R1 plus R2 plus AVOL into R1. So, we get the voltage gain of the feedback amplifier, or this is the non-inverting amplifier, as V naught by Vs, which is denoted by AV, and that is equal to AVOL into R1 plus R2 by R1 plus R2 plus AVOL into R1. Now, doing a little further simplification, we can write down this gain AV as AVOL divided by 1 plus AVOL into R1 by R1 plus R2, because here what we are doing is we are dividing both the numerator and denominator by the term R1 plus R2. So, dividing by R1 plus R2 this term, we get in the numerator free of R1 plus R2, and in the denominator it is, this part will be 1 plus AVOL into R1 by R1 plus R2. Now, this R1 by R1 plus R2 is given a name beta, and this is known as feedback factor. The feedback factor means this is the resistive network from the output to input. If we consider the output to input network, that is this part of the circuit, we see that the output and input are connected by this network of R1 and R2 resistance. That is why this is known as the feedback factor R1 by R1 plus R2. Then we have another expression for this gain AV, which is given by AVOL by 1 plus AVOL into beta. R1 by R1 plus R2 is beta. Now, the gain has an expression given in this form, where AVOL beta is known as the loop gain. It is having a name loop gain because it is coming from the loop. Now, in this expression of AV, the difference between what we earlier got using ideal OpAmp is coming from the denominator term 1 plus AVOL beta. Now, if we have AVOL beta very large as compared to 1, then what we will be getting is that the gain will be given by now AVOL by 1, because if this AVOL beta is very large as compared to 1, then I can write AV equal to AVOL by AVOL beta. So, these two cancel, that means I get 1 by beta. So, 1 by beta is what? 1 by beta is R1 plus R2, R1 by R1 plus R2. So, 1 by R1 by R1 plus R2, that is 1 by beta. That means it is equal to R1 plus R2 by R1, which is nothing by 1 plus R2 by R1. If we now recall the gain of a non-inverting OpAmp, which we earlier got using ideal OpAmp consideration, it was 1 plus R2 by R1. So, that 1 plus R2 by R1, where R2 is the feedback resistance. If we look into this circuit, R2 is the feedback resistance from output to negative, and R1 is the resistance from negative terminal to ground. So, we have the ideal OpAmp consideration giving that value, which is ideal. AV will be ideal OpAmp consideration gain AV, and this is obtained if this condition of AVOL beta is very much greater than 1, that is satisfied. Otherwise, we will be having a gain which is not given by the ideal OpAmp gain 1 plus R2 by R1, but it is given by this factor. So, if we consider exactly the practical case of a non-inverting OpAmp, we have the gain given by this term. So, the closed loop gain or the closed loop effect is coming here, and another factor to be notice here is that the difference voltage. Now, what is VID? VID, if we consider in the circuit, this VID equal to Vs minus V2. So, replacing V2, we get it is equal to Vs minus V0 into R1 by R1 plus R2, and that can be written as Vs minus R1 by R1 plus R2 is beta, the beta V0, and Vs minus beta into V0 can be written as AVOL Vs by 1 plus AVOL beta, and this simplifies to Vs by 1 plus AVOL beta. So, the difference voltage VID, if we see, it is equal to Vs by 1 plus AVOL beta. So, now in this exact circuit using the practical OpAmp consideration, one thing is to be noted is to notice here is that the feedback which is there is a negative feedback, means to the voltage applied voltage Vs, the feedback voltage is adding up in a negative way. If we consider the feedback voltage, what is the feedback voltage? Means the voltage which is available due to the feedback loop. If we consider this voltage is V2, that is the feedback voltage available because of this loop. So, now if we consider the whole circuit again and see it from that point of view, That means where this feedback voltage is being added up and what is the polarity of this feedback, then we will understand how negative feedback is happening here. So, here if we look into the circuit, you are applying a voltage Vs. This block is the OpAmp block, which is having this Ri resistance, and the gain is AVOL, and this resistance R naught is very small, basically that is why we are using that approximation that this is 0. So, that is why it is 0. Output voltage is V naught. Now, we are having a network of resistance coming from this output, and it is having R naught, R2 and R1. Now, the voltage across R1 that is being added up to the input at the negative terminal, and what is this voltage across R1? Let us name it as the Vf or feedback voltage, and that voltage is equal to beta times of V naught, because that we have seen here. What is this voltage? V naught into R1 by R1 plus R2 is the feedback voltage, and that can be written as V naught into beta. So, beta V naught, this much of voltage is the feedback voltage available here at this point. Now, this voltage is applied and it is connected at this point, which is negative of the OpAmp. So, if we consider the input side, we are having a voltage Vs and we are having another voltage Vf, but the polarities are such that this point is positive, this point is negative, because this point is positive and this point is actually ground. So, here the voltage Vf and Vs, if we look into the polarities, these two polarities are in such a way that Vf opposes Vs. If we consider this voltage at this point, it is Vs minus Vf is the voltage at the input of the different input of the OpAmp VID, because that is very clear from here. If we consider this loop, this loop uses Kirchhoff's voltage law, Vs minus VID, this point is positive with and this point is negative. So, it is minus Vf, that is equal to 0. So, what is VID? VID is equal to Vs minus Vf. That means, the voltage at this point, that is Vf, which is the feedback voltage available because of this feedback resistance R1 and R2 loop, it is negatively adding to the input or supply voltage Vs. That means, the voltage available at the input terminals of the OpAmp is now Vs minus Vf. So, this is the reason why this feedback is called a negative feedback, because negative feedback is meaning is that the feedback voltage is negatively added up to the input. So, the actual applied voltage is Vs minus Vf, where Vf is coming from the feedback part. So, due to this negative feedback, we are having that the gain of the OpAmp, which is ideal gain, should be AVOL, but this is not AVOL now, it is AVOL by 1 plus AVOL beta. But of course, if this quantity AVOL beta is very high in comparison to 1, then we will be getting that ideal non-inverting OpAmp gain 1 plus R2 by R1. Now, if we again look into the circuit and find out another important parameter, which is the input resistance. Now, in this circuit, the input resistance, which is shown as Ri, that is modified now in the actual circuit. That means, the OpAmp input resistance, which is Ri, it will be not now having the same value of Ri, it will be also having a different value. So, to know that, to find that out, let us not name it as Ri, let us name it as RID, that is the input resistance of the OpAmp. But now because of this negative feedback, effect of this negative feedback on the input resistance, if we want to find out what will be that. So, let us find that input resistance and the effect of negative feedback on the input resistance. Effect of negative feedback, if we find out, so now again same circuit we are considering, only we are naming it as RID. So now what will be the input resistance that can be found out if we again consider this circuit? What will be this input resistance Ri of the circuit? That Ri can be known as, suppose this at these 2 points we are having the resistance Ri, we want to find out what is the input resistance of this circuit, then it will be simply Vs by Ii. So, Vs by Ii gives the input resistance of this whole circuit, the input voltage by input current, Vs by Ii, that is actually Ri. In order to find out now Vs by Ii, that we have to find out, that is the input resistance. Now, what is now Ii that we have to find out? So, if we look into the circuit, what will be Ii? This Ii input current, it is nothing but equal to Vs minus V2, this is the voltage here, this is the voltage here, divided by RID. So, Ii equal to Vs minus V2 by RID, because this is the current which is flowing, and the current which is flowing between these 2 points, the voltages at these 2 points are V1 and V2. V1 is nothing but Vs, and what is V2? V2 is the feedback voltage basically here, which is given by V0 into R1 by R1 plus R2. So, assuming that same approximations, that the input resistance RID is very large and neglecting this current I dash, which is neglected to be equal to 0. So, we get I equal to this, and what is V2? V2 is equal to actually the feedback voltage V0 into R1 by R1 plus R2, and that is nothing but beta times of V0, because this part is beta. So, now we can write down that equal to again beta V2 equal to beta times of V0. Now, what is V0? If we look into this circuit, what is V0? V0 is equal to AVOL VID, and what is VID? We have already found out VID to be equal to this value, Vs minus this term. So, using those values, we are writing V0 by AVOL VID, and replacing this VID by AVOL VID, and that is equal to beta times AVOL into what is VID, that is again replaced by this term, that Vs minus beta times of V0. So, we write again what is Vf beta times of AVOL Vs minus Vf. So, what is this? This beta VAVOL into Vs minus Vf basically. So, from here what we will be getting is that finally Vf is obtained as AVOL beta by 1 plus beta AVOL into Vs. So, now we can write down the current II equal to Vs minus AVOL beta by 1 plus beta AVOL into Vs by RID. So, now simplifying this further, we get finally what is Vs divided by, if you simplify it further, it will be in the denominator it will be 1 plus beta times AVOL, and in the numerator 1 plus beta times AVOL minus beta times AVOL. So, these two cancel, what will be remaining is simply Vs. So, Vs by 1 plus AVOL beta into RID. So, Vs by II, that is our input resistance, that is equal to 1 plus AVOL beta into RID. So, if we look into this term, what we get is that the resistance of the OpAmp, what was RID, that is multiplied by a term 1 plus AVOL beta. For example, suppose AVOL for an open loop voltage gain of an OpAmp is say 2 into 10 to the power 5 and beta value is say 1 by 100, and beta means coming from that resistive network. So, that resistive network has the beta value, and that is equal to R1 by R1 plus R2 is beta, and that is given as 100, 1 by 100, and what is RID, for example, is say RID is equal to say 2 megohm, and it is typical value of 741 IC. So, now what will be this RI? It is equal to 2 into 10 to the power 5, almost AVOL beta becomes 2 into 10 to the power 5 into 10 to the power minus 2 plus 1, almost this is equal to 2 into 10 to the power 3, 2 into 10 to the power 3 into 2 megohm, and that is one term I am just neglecting because it is very small. 1 is very small compared to AVOL beta, which is equal to 2 into 10 to the power 3. So, what will be the RI value? It is 4 into 10 to the power 3 megohm. That means 4000 megohm becomes the input resistance of the OpAmp. When the OpAmp resistance was 2 megohm, but due to the negative feedback, the input resistance of the whole network or whole circuit becomes 4000 megohm. So, now from this discussion we have seen that the input resistance is becoming very high because of negative feedback, and similarly we can also show that the output resistance becomes even smaller than the output resistance of the OpAmp. So, because of this negative feedback, there is an effect on the voltage gain as well as the input resistance and output resistance of the whole amplifier, and these are changed from the voltage gain which is open loop voltage gain of the OpAmp or input resistance or output resistance of the OpAmp. We have even higher value of input resistance and we can show that the output resistance becomes lower than the output resistance of the OpAmp only. So, because of negative feedback this effect is obtained. So, because of practical considerations of the OpAmp, because of the non-ideal effects or parameters which are present in the OpAmp, when we use a practical OpAmp in a circuit like we have seen in a non-inverting OpAmp, similarly it can be shown in other applications also, that the negative feedback effect is modifying the parameters of the circuit like voltage gain, input resistance, output resistance, etc. And this is negative feedback, and there is another type of feedback, positive feedback, which is giving you oscillators, and that we will be discussing later.